Give a little bit of the Western background, kind of how we approach fire, and therefore it's also kind of a microcosm of how I teach fire behavior, fire ecology here on campus. Of course, it's a very compressed view, so buckle your seatbelts, and you're going to think I'm bad until Frank gets up here. So that's the plan. Well, we have to start, of course, with the fire behavior triangle itself, because basically part of the important message for you today here is that this message of it, it's just physics. When you come right down to it and you light a particle that is burnable, and you blow a certain amount of wind over it, and you have it at a certain temperature, and maybe it's sitting on a slope of a certain percent and all, it burns that way today, and it will burn that way if all those conditions stay the same, tomorrow and the next week and the week after that. And there is a wealth of it. We've been basically using these same physical equations that regulate burning in the science literature and all for a good 40-some years now. There have been some major efforts to try to revise those equations and update them, and they find time and time again that you don't need to bother because the physics there are still the same out there. And so what this produces is a set of really good models to look at how the weather and the topography and the fuels and even fairly complex fuel beds out on a hillside, how that burns out there. And those are wonderful tools. I expose my students to them. They just love it. They spend hours in front of their computers running these models because they are so fascinating. And then you can take that and expand that up to the next level and put in a whole GIS layer and complex fuel beds and how it might change from a southern exposure to a northern exposure, and some different winds, a windy day and a not so windy day, and a dry day and a not so dry day, and all those kind of things, and burn fire over entire landscapes. Those models are even more fascinating. And it's a wonderful, wonderful tool that is set out there. And part of the foundation, since we have very little control over the weather and the topography, is that we have some control over the fuels, and we can play around with that fuel component that we have and look at how that's going to impact fire spread, fire behavior on a grander scale. A little bit with these ground fuels, some with the crown or aerial fuels. The big player here is in surface fuels, and we're interested in that. And fire is going to proceed through this area along the surface, and every once in a while it'll blow up in here, and every once in a while it might burn something that's down actually in the ground. But by and large, surface fire is really where it's at. And of course, there is the connection between surface and crown fire, the surface and the aerial fuels, ladder fuels. That term maybe has come up already today, or may come up with Frank in there. And we have to take apart those surface fuels a little bit because we probably end up talking about the fine fuels, the really small stuff that dries out quickly, burns quickly, and the larger pieces that dry out more slowly and burn more slowly. They have different implications out there because the fires themselves and how we characterize fires and how we're going to talk about fire, and Frank's going to talk about fire, is really categorized by these fuels. And so you have the ground fires that correspond to the ground fuels. Crown fire, of course, very spectacular, but relatively rare in the bigger picture of things. In most of the fire that we're interested in, most of what's happening out there, most of what we use as natural resource managers is really surface fire. And there we are using the fine fuels to regulate spread, so how fast it moves and how high the flame lengths are, how much heat is given off. And then the coarse fuels are regulating the real severity, how much total heat is produced and how long is that heat there, because that translates into the severity out on the hillside. And we'll come back and talk to that in a minute. So I've made the point that it's just the physics and we have the good models. The problem is the real world. Because despite the best information that we have about fuels, and me putting 1,000 graduate students out on the hillsides, measuring those fuels, very detailed, the best weather stream data that NOAA can provide, the best topographic map I can get from the military, that can look at ants crawling on the ground and all that kind of stuff, feed that all into a supercomputer and run the models, I still cannot recreate real fire perimeters as they happen out there. There are chaotic patterns out there that just cannot be accounted for. And for me, it's what makes fire absolutely magical, because it is completely unpredictable from that. So we've covered the whole span from completely physically predictable to impossibly chaotically wild and crazy. And so it's just a wonderful, wonderful field to work in. But that whole range and our understanding of that whole range really defines our understanding of these fire regimes and fire ecology. And so if you look at this array of forest types, at least in the Pacific Northwest, it ranges across temperature and water. So temperature and water kind of relationships that we have out there. And we have this classic ponderosa pine type that has very frequent fire that comes into it. A lot of these forests actually could be more accurately categorized as savannas or even grasslands with scattered individuals or clumps of trees in them, at least down on the driest ecotones. So out this way, they become extremely low density, but a nice fine fuel, other people call it grass, I'll call it fine fuel layer out there that's carrying fire through it on a very regular basis. And it's really what defines this classic ponderosa pine. And this is all throughout the West. So it's California, Oregon, Inland Empire, all of that area. As we move out this way, it gets dry enough and often warmer as well moving up here. So at that point, the fuel accumulation rates and total amount of fuel and how quickly it regrows following disturbance actually limits how often fire can come in. And so fire becomes less common, but we can go centuries out up in here and accumulate enough fuel over centuries and get enough crown closure in juniper woodlands that then they burn largely as stand replacing events. But it's severe for those systems, but relatively uncommon. As we add moisture into the system, we get more fuel, but less regularity in the burning pattern. So we get into the dry mixed conifer, Douglas fir, sugar pine, often some hardwood mixed into those forest types as well. And there, where we had burning intervals of maybe less than a decade, in this area, we get to several decades, fire coming through these forests every several decades. And as we're adding productivity into this system, the fuels are accumulating at such a rate that some of that fire, it's never uniform, some of that fire is high severity, some of it is moderate severity, some is low or no severity. And in fact, this mixed conifer forest type could be called a mixed fire forest. There's that close of a linkage to the fire dynamic. And then as we're cooling down and adding more moisture, so everything from the temperate rainforest to a snow-filled subalpine kind of forest type, there we can have the fuel accumulations, but we don't have the burning conditions happening very regularly. And so again, we go to something that is very infrequent in terms of how it burns, but with the fuel accumulations, it burns quite dramatically and in a stand replacing fashion. And so we have the whole spectrum here aligned along a diagonal axis of productivity in there. And that defines, so this fire dynamic and that productivity and other characteristics that are going on out there ecologically define the composition, the structure, and the function, right? And the structure is both the living and the dead structure, and the wild and craziness of fire, creates diversity in both a horizontal and vertical sense in these stands. And it's very closely linked to that fire behavior itself, the post-fire environment, and how that sets the stage for the next fire. As a matter of fact, my teachers told me wisely that the post-fire environment is the pre-fire environment. So think about that one later this afternoon. Function. Fire is a big function, but so is the nutrient cycling, some of the longer-term hydrologic processes that are put in place by the fire disturbance itself out there. All of these forces create these broad categories of what we call fire regimes. We've already talked about that frequency and how that ties to productivity. How often does fire come in? And that has an extent part of it. There are large expanses of ponderosa pine, like northern Arizona, that could burn tens of thousands of hectares in one given event, but all as a relatively low intensity and low severity out there. And otherwise, in that mixed conifer, a small pocket of ponderosa pine can burn as low severity there as part of that larger mixed conifer complex that includes some high severity areas in there. And so that whole, as you get into that part of the system, you pick up this complexity. So there's the temporal pattern tied closely to seasonality, but also the year-to-year variability and the Pacific decadal oscillations and all of those kind of things, the very large temporal patterns. And that creates, well, I've been talking some about the small-scale spatial patterns here, but there are large-scale landscape patterns that are created by this fire dynamic as well. So that's kind of the fire behavior 101 and sets the stage for looking at something like the B&B complex fire. That the ignition point was actually here, either a lightning strike or a black helicopter event set up for President Bush's visit in the signing of the Healthy Forest Restoration Act. But it flared up here. All of one day it goes up and back and sets up this whole pie slice shape here. 2 days, weather driven. And then for a good 2.5, 3 weeks thereafter, the rest of this perimeter burning through a fuel bed, at that point just too big for people to get their arms around. And it basically burned until the snow came. So two different dynamics going on there. And important to creating this is one of these areas with mixed severity. Some areas that burn very hot, but then these areas where the density wasn't too high, or this is an area that actually had a fuel treatment put into it. And there is some surviving green tree component. But there are parts of the B&B fire that were many hundreds of acres without a living green tree left in them. And for some forest types, that's fine. Unfortunately, it was in some areas where that kind of fire behavior is unprecedented and now has happened for the first time. And then a whole lot of areas where there was little to no mortality within that larger perimeter that I just showed you. So here is the image of that first day with the fire, bringing the smoke over here towards Corvallis and the coast. The weather frontal system comes through, and it goes almost exactly the opposite direction the next day, and that's what creates that pie shape. And that's what, in terms of deployment of suppression forces and all that kind of stuff, they were just completely overwhelmed by that whole situation. So that fire, so we have this unusual fuel accumulation now after 100 years of Western settlement into this area, and we had maybe natural or maybe augmented by this fire suppression activity, but there was a lot of spruce budworm and pine beetle activity up there prior to the B&B fire. There were a lot of people that I knew that kept saying for the Santiam Pass area that it's a disaster waiting to happen. It's a disaster waiting to happen, and then it happened. Well, not really a disaster, but it was there, and that's kind of the current stage. And I want to contrast that with a 1901 image for a surveyor that was coming in for setting up the Cascade Range Forest Reserve. What would become partially the Willamette National Forest and partially the Deschutes National Forest. And so in this map, the lighter colors are low density, low merchantable value. And so what you would recognize as a Douglas fir forest and an old growth forest are these darker shades of green, lots of standing timber that Mr. Plummer mapped as a resource, a reserve resource that we could come back to. And some decent ponderosa pine over here down and around Black Butte and all that kind of stuff, but a pretty clear elevational band here in that dry mixed conifer area on up to the snowfields and all. That was very low density, low merchantable value. And in fact, it's hard to see on this map, so I'm circling about a third of them where Mr. Plummer actually mapped everywhere from 50 to 60 acre burn patches. I would assume within about 10 years of when he rode through on his horses that these areas had burned. And then some several hundreds to 1,000 acre burns. So this is only about a third of them. There's another big one right here and one there. You know, I could circle them all, but then it would become a very noisy kind of map. But they're all up there, and you can come take a look at it later. And this is kind of what that area would have looked like. This is an 1896 or an 1898 photo. How they got the dog to stand still, I have no idea. But they got it. But it shows some of this kind of, a lot of burned over area, but you know, a completely skipped area there, some other green, younger forests back here in there. So it was large burns. You know, it'd be understandable what Mr. Plummer was seeing there. There is the B&B fire. You know, it's 4 to 5 times the size of the biggest fire, you know, in 1901. And so the complexity, the continuity, the total size, total extent, completely unprecedented. And so that's part of what we're up against now. And in fact, we're just bound to have another one of these. This whole area down here around the Davis Lake fire, those of you familiar with this area, it's pretty ripe to get ready to burn again out there.